Okay then, so we know this Mitchell-Benabou language now, and we want to understand what the other important notions in logic are. So let's start with there exists. So there exists an x such that phi, and we define this like this. For all w, we have that for all x, when phi implies w, then that implies w. So this statement is equivalent to saying that there exists an x such that phi. For example, we could think about phi as 1 plus x equals 3 in numbers. And so we're interested in saying, is there a number that satisfies this, for example? So why does this work? And what's it say? Well, the way I think of it, given a fact w, if w is true whenever r is true, then there exists an x such that phi holds, where r is saying that if phi holds for a given x, then w holds. So r is basically saying that when phi of x implies w for all, it's saying that phi of x implies w for all x. So let's prove this now. So suppose there exists an x. Well, we'll argue why it works classically at least. So when there exists an x such that phi then for any given w, when we sort of pass over all the x's, for one of the x's, phi of x will be true, and that'll imply w. So that means that we will get w implied. So if we have that there exists an x such that phi, then given any w, when we look at, I mean, if this statement's true, like that, then when we go over all of, well, if this statement r holds, then when we go over all of the x's, we'll find one where phi of x is true, and that'll imply w. So then that r does imply w, okay? So this is correct when there exists an x such that phi. Alternatively, if there does not exist an x such that phi, then what about if w is a true statement? What about if it's just true? Well, when we work over all the x's, we'll always find that phi of x is false, because if we assume that this is incorrect, that there doesn't exist an x such that phi. And so the statement for all x, phi of x implies w, is false, because there won't be any x such that phi of x is true, whereas w is constantly true. So then r will be false, but then it's not true that r implies w for the case where w is true. So this will fail if there doesn't exist an x such that phi. So this does seem like it's equivalent to saying that there exists an x such that phi. The definition of false is very interesting. False is saying that for all w, w holds. So false is saying that everything is true, okay, which is obviously not correct because we can take w to be false, okay. So that's our definition of false. Our definition of not, so not phi, means that phi implies false. I think we can also define it as the classifying arrow with this arrow false. But anyway, the other thing to define is or. Okay, so phi or w is equivalent to saying this: for all w, when we have that phi implies w and psi implies, so we're saying that, sorry, this is a statement which goes this says that phi or psi, and I'm saying this is equivalent to this statement here, that for all w, if we have that phi implies w and psi implies w, then those two, both of these, this and this, we're saying that for all w, we have phi implies w and psi implies w implies w. Okay, so I mean this works because let's suppose that one of these is true, either phi or psi. Let's say phi. Okay, well, if phi is true, then if we have that phi implies w and psi implies w, then that does imply w, because we've got, you know, they both imply w. So if one of them is true, then we get w. All right. On the other hand, if they're both false, and we take w to be true, then we have the false implies true, that's false, and false implies true, that's false. False and false is false, and this is false implies true, which is not correct. So this formula fails in the case where phi and psi are both false. So if either of phi or psi is true, then this formula works. If they're both false, it fails. So it's equivalent to saying phi or psi. Okay, so there we have it. We have a definition of or, a definition of there exists, a definition of false, and a definition of not. And basically, we can also define and as the classifying arrow of true, true. And I've said how we can define there exists. Sorry, I've said how we can define and. Sorry, all, for all. I've said we can define for all as, for all x is the classifying arrow of the name of true x, and the syntax involving there exists like this is very similar. to the syntax for that we use for all. It's basically equivalent. So we have all of the different well, there's also implies, but I'll get onto that. But yeah.